When it comes to an active shooter scenario, every second counts. Law enforcement needs tools that are not only reliable, but also cutting edge. That is why we have created the next generation breaching tool.
Hello, my name is Brooke Risley. I'm a mechanical engineer and the team lead for the 25006 Active Shooter Scenario Door Breaching System project.
My name is Ethan Yock, and I'm an electrical engineer and the procurement lead.
Hello, my name is Ian Harrell. I'm a mechanical engineer and I'm also the mechanical lead for the project.
Hello, my name is Fado Muteri and I'm an industrial.
Hello, my name is Emily Ayala and I'm the systems engineer and the integration lead.
My name is Jimena Peregrino and I'm industrial engineer and the documentation lead.
Hello, my name is Daniel Wagmuth and I am a mechanical engineer.
Current breaching techniques prove to be inefficient by requiring excessive force input from the officer, creating long breaching times, officer fatigue, and vulnerability of the officer in the line of fire. The commonly known battering ram, which is used to breach inward opening doors, can take up to 4 minutes to breach a singular door. And the less well-known Halligan, used to breach outward opening doors, can take up to 10 minutes per door. There is a demand in the breaching tool market for a tool that is operable by a single officer, regardless of size or strength, can breach any level of security door in under 2 minutes, and can breach both orientations of door in one single tool. The key system requirements derived from our customer careabouts and applicable standards are as follows. The tool shall generate a total force of at least 503 pounds. The handheld aspects of the system shall weigh 35 plus minus 10 pounds. The tool shall breach the door in under 2 minutes, and the operator shall be able to properly operate the device after no more than 1 day of training.
The team began by deriving the force required to break through a standard steel reinforced door frame. The governing equation for the maximum deflection of a cantilever beam was utilized to find the force that would break the door along with the moment of inertia of a steel hollow rectangular beam to model the door frame. The team used the Steel Door Institute standard A250.8-2023 to get the required measurements for the equation. The design utilizes a 5,300-pound column-load hydraulic actuator enclosed within student-designed steel and aluminum parts that are able to apply the force generated by hydraulics actuator to the weak points in the door. The actuator is connected via a 4,000 psi rated hydraulic tubing which pumps hydraulic fluid from the Vevor 3,000 psi pump. The pump houses a 4-position 3-way valve which prevents overpressurization of the system during extension and retraction.
The so-called teeth of design were designed using SOLIDWORKS 2023. The program ANSI was utilized to perform finite elemental analysis on the system to ensure the teeth can withstand the predicted 500-pound reaction force required to breach a steel reinforced door. The aluminum handle was designed to be ergonomical to the end user and encompasses similar gripping techniques to familiar tools and weapons utilized by officers. The footbar subsystem is designed to withstand body weight applied by the officer when using the tool in different breaching configurations. Finite elemental analysis was performed to ensure the strength of these components. The aluminum shell allows for the attachment of these components and provides a sleek, encompassing design. Padding, as well as the stabilization bar, is used to properly secure the actuator inside its aluminum housing.
The 12-volt DC battery which powers the design is housed in the backpack section. The connection is made using 3/0 gauge wire to handle the high currents. The motor can draw up to 200 amps, while the 3/0 gauge wire is rated for 285 amps, giving us a factor of safety of 1.425. The 12-volt battery also activates the solenoid valves based on the position of the operating switch to allow the oil to flow in the extend and retract directions. To mitigate heat produced from the motor, the backpack will have ventilation ports to allow the heat to dissipate. The wiring schematic can be used to represent the system's electrical assembly. The two normally open push buttons control the signal to both the up solenoid and down solenoid. There are two common wires attached to both buttons that will send a signal from the battery to the DC contactor that acts as a relay to control the DC motor.
The design can be summarized at a high level using our system block diagram where we can break up the 4 subsystems into their respective categories. Our first minimal viable product focused on integration of the hydraulic and the electrical components, allowing the team to understand how the two mesh together and ensure we can succeed when it comes to the final prototype. The second minimal viable product focused on weight reduction while improving factor of safety of the teeth components. Through our redesign, we were able to eliminate roughly 1 pound from each tooth and improve their safety factors by 400%.
One main pitfall of current breaching tools is the requirement of 2 or more officers to properly set the tool in place. This is often due to the small gap present near the point of attack at the locking mechanism. In these models, we can see how the door is breached at both orientations. For doors opening towards the user, our tool uses an innovative approach that applies hydraulic force to the bottom of the door. To firmly position the tool into place, the operator can use their body weight on the footbar component to position the teeth under the door. By extending the hydraulic actuator, the door is offset with the bending of the hinges, creating a point of attack at a weak point by the locking mechanism. A handy wedge secured on the shoulder strap of the backpack can be used to hold this position. The tool is now inserted into the door where it can deform around the door and the deadbolt to breach the door. In the second orientation, the device is simply inserted in between the door and the frame. By extending the actuator, the door is breached, breaking the latter half of the door frame.
The team used the following verification table to record and document the verified requirements. The methods of test, inspection, analysis, and demonstration were used to verify various requirements. For the weight limit requirement, the team used a weight book to track and monitor the weight of the handheld system using estimates from SolidWorks for design parts and data sheets for those parts bought from suppliers. After receiving each component, the team would weigh and record the weight. Our final prototype came in at a weight of 30.8 pounds, leaving us with a margin of 15 pounds. The team has procured both training manuals for user operation and integration manuals at this time. The training manual includes images, models, and text using familiar breaching terms already used in other breaching techniques to ensure understanding for operation. The training manual was successfully read and understood in less than an hour, allowing the team to pass this requirement. At this time, all requirements have been tested and 8 out of 13 requirements have passed on the first round of testing. The team plans to implement small design modifications to improve the design and achieve passing margins on all the remaining 5 requirements before design day.
The finished deliverables to our sponsor include documentation such as our comprehensive final report, training manual, and the integration manual, as well as the final prototype version we have created.
Throughout the design and prototyping process, the team learned many valuable skills and ways to improve our design. Upon our initial assembly, we noticed more leeway than expected from the hydraulic cylinder inside the shell component. To alleviate this, we utilized 3D printed components to improve tolerances and minimize unwanted movements. The team utilized the expertise of professional machinists at the University of Arizona to receive feedback and corrections on engineering drawings. We were able to reduce machining times and costs by implementing their feedback on machined parts. This also allowed us to emphasize safety as we focused on part integration and not machining.
We want to extend our gratitude to our sponsor, the University of Arizona Police Department, and Sergeant Joseph Berriman for the help and support throughout this project. We also would like to thank our mentor, Jeffrey Wolski, for his expertise and support along the way.